See? Cool. Vincent, you're on.
Okay, great. Hey, how's it going? Today, we're going to talk about generative models, which is basically figuring out how to start from a seed of some random number, some noise, and generate some type of object. So, what I want to ask you to talk about this, I went through the chapter 20 of the Deep Learning book, and I think it's really good and worth a read. It's really technical at parts, so I kind of got away from some of that presentation. There's really no way to get around it than I think, you know, going through all those formulas and stuff. But I tried to do a good job of doing some kind of like high-level summaries of the concepts. Hopefully, if you're familiar, you'll learn something new. If you're brand new to kind of some of these statistical models, I'm kind of hoping to just like share some intuition about what's going on high level. So my background is in statistics and finance, so a lot of like time series and stochastic calculus. So I'll think about everything like probabilistically, I think, when it comes to math. And then my notation probably comes from there. I think, you know, deep learning is really tough because it's a hybrid of so many different fields. So the notation can be a little bit all over the board. So definitely, if anything, like if any single symbol on here looks confusing, ask me and I'll tell you what I think it means, you know, how I interpret it and why I put it there. But sometimes, you know, people have a little bit of nuanced notation. And just because it's a confluence of kind of like statistics, computer science, pure math, linear algebra, the notation can get a little bit jumbled. So first,
hold on, can we pause for a second for saying that they're having an echo issues online and I can't hear it. So I don't know what's going on there. Is your Hangouts, can you make sure that the sound is off? So I can hear both this double, like, it's like, oh, this is better. And that sounds better. Can you say something?
Yeah. Is that better now?
That's better.
Okay.
Yeah, I don't know, whatever you did worked.
Cool. Okay, great. So I guess first let's talk about what's on the screen. So this is an example from a generative model that came out in May, and it is kind of the state of the art, I think, for generating pictures of faces. You know, in terms of what's publicly available. So these are all fake faces. They are really glossy because they're on a trained on a data set of 360,000 celebrity headshots. So if you're wondering why they don't look like kind of normal people today, that's why. So, you know, it's a function of what you're training on. And what we're trying to do with these generative models is we're trying to learn an unknown probability distribution, and then take a distribution we know really well, like for example, Gaussian or normal distribution or uniform distribution, and make a function that maps from one to the other. So what I'm saying with these equations on the left is that we have some function f that is a function of some variable x, and x is 64-dimension uniformly distributed between -1 and 1. So you can kind of think of it like a cube in a really high dimension space, and we can sample, you know, a uniform distribution is really easy to sample from, and then we have this function that will transform, if the function works well, it will transform any number into a face. And that function is parameterized by theta. So, you know, it's easy to write f of x, but that function has like 17 million parameters in this model used to calibrate these faces. So there's a lot of linear algebra going on. You can think of it by and large as you know, sets of matrix multiplication with ReLU nonlinearities applied in order to replicate the complex function that would generate some faces. And then, so I talked about those other two line items, but this one basically says that we're going from something in 64 dimensions to an image, which is 128 pixels by 128 by red, green, and blue. And that mapping is, you know, an example of what we're trying to do when we talk about generative models.
Yeah, what is the 64 dimensions?
So that's what they chose. So this is this BGAN, or boundary equilibrium GAN model, and how did they get to 64? I don't know. I mean, it's pretty common to use powers of 2. Something like, if you're trying to describe the space of all faces, you probably need more than like 5 or 6 dimensions. Would 32, 64, 128 work best? I guess it's just kind of a function of, you know, your choice, how much time you have to train something, and how kind of specific you want it to zero in on things versus, you know, how vague you want it to be. This model is, you know, pretty awesome for generating faces. It has some pretty interesting ideas in terms of how it works. So I guess the trajectory today, I'm going to talk about first something called variational autoencoders, which are utilized in this model. A GAN, or a generative adversarial network. So first, we're going to talk about a basic variational autoencoder, then a very basic GAN, and then kind of some hybrids in between. And I honestly wanted to talk about Boltzmann machines as well today, but I kind of ran out of time preparing, so I didn't really get to that. We can talk about it a little bit if you want. I just don't have the slides prepared, I thought, to make some of these. So yeah, so this will be the order, and maybe we'll take a little bit of a break after we talk about the GAN, the first generative adversarial network. So I guess, what does it take to make a generative model? One of the big things is you need a whole bunch of examples of something, like lots. You know, it's not a hard term. Like, how many examples do you need? Basically, the more the better. What type of data it is. More examples will help you learn things better. Images are the classic example because they're kind of static. Like, I think humans are really, really good at perceiving images, especially in terms of like static data that we can just look at. Audio is tough because, you know, it's time dependent and so forth. But technically, these generative models could be used for pretty much anything. So definitely audio. Something like, if we get to Boltzmann machines, we could talk about movie reviews. For that Netflix competition, in terms of like, if you have a whole bunch of people that have reviewed some set of all of the movies out there, how do you predict how they would review other movies? That could be thought of as a generative model, so we can talk about that. So yeah, you need lots of examples of whatever you want to generate, and then you need some way of learning embeddings about that. So some way of relating different examples to each other. So one simple way we can talk about for doing that would be an autoencoder, and then there's kind of other approaches for doing it that are a little crazier. You need a random number generator at some point, and then you also need something to numbers onto, you know, some high dimension manifold. And you also need something to evaluate your examples, and then based on that evaluation, you'll be able to improve your embeddings and improve your generation model. Is the audio good? Cool. All right, so first, just a review of the basic autoencoder, which is basically doing lossy compression. So whenever you have that have some things in common, there's redundancy. So here I have some initial example has like a dimension n, and then we're going to compress it down to some m, which is less than n. And basically, it's just trying to get rid of the redundancy, but then ultimately, when we decode, we'll be able to reconstruct our initial example with high fidelity. So be it handwritten digit, an image of handwritten digits or whatever, it's like, it doesn't matter what the data form is. You're just trying to compress something to a latent space or an embedding space that you could then regenerate it from. So all of the information contained, ideally you want to do it lossily, but it's really only interesting when it is lossy, when you're by definition losing some information, but trying to reconstruct as much as you can. So you really want to put things through a bottleneck to, otherwise you just have a photocopier and it's not that cool. And then, yeah, so different ways to do loss. Pixel-wise L2 norm would be the most common thing, where you're just looking at differences between the individual pixel values. Another pretty cool one is to think of cross entropy, which is informed by information theory, where you're looking at p log p, or you're kind of modeling it as either, let's say you have only black and only white pixels, or you have gray pixels, and you're thinking of it probabilistically that gray is kind of representing some probability of being black or white. Use, you know, all your standard information and entropy equations, and it's a really interesting loss function to see how things would vary between looking at an L2 norm or looking at cross entropy. So yeah, that's a basic autoencoder. But the thing about that is the embeddings will have, it's tough to sample an embedding space because you have no constraint saying that embeddings need to be distributed in any way. So what a variational autoencoder is it utilizes a lot of stuff from, basically the thinking is grounded in Bayes, which is all about inference. And you use regularization functions to make your embedding space have certain characteristics. So this one encodes all of the handwritten digits down to just 2 dimensions. So in theory, you can see of the 10 potential handwritten digits, I took this from a blog post where they assigned each of those digits a different color and then would all be represented into an embedding space. So
I'm
yeah.
just curious what, oh, you put the labels there too. There's like some clusters are, some are like on top of one another.
Yeah, exactly.
I'm curious which ones are failed ones.
Um,
The red flags and the light.
Yeah, so I wouldn't necessarily call it failure because the task isn't to segment here. It's actually to just try to reproduce images with high fidelity. You're absolutely right, though, that it's like 9, 7s, and 4s. So kind of this region seems to have a lot more overlap, whereas like 0s and 1s would be more differentiated. And then in here, we kind of have some fake number that looks like a phi, that looks like a 0 with a 1 through it, which would be this gap of where no embeddings. But so the regularization function that causes the embeddings to take this shape is you basically think of everything probabilistically. So if we go back to the encoder, in this model, it's specifying a point, z. It's specifying exact coordinates of where it would want the embedding to go. Here, the way this is accomplished is by you specify a point around that point. So it's like you have a dart and you say where you want to throw the dart and how much leeway it can have to move around. And basically, you're penalized to the extent your embedding deviates from 0 and to the extent you don't accept variance and where the embedding could go. So that allows us to do a lot of Bayesian inference. And basically what this does is it maximizes the probability that something sampled from a unit Gaussian would result in a real handwritten digit. And it actually doesn't guarantee that, but it specifies a lower bound on that. And we'll go into that, but the groundwork is based in Bayes' theorem, which is all about inference. We can do a toy, like it might be a good idea. How comfortable are people with Bayes? Does anybody have no idea about what Bayes' theorem is? Does anybody should we just do a little example or should we skip it? Yeah, cool. So Bayes is when you have 2 things that are related, so 2 things that aren't totally independent in a probabilistic sense, by observing one, you could learn some things about the other. This is kind of a silly example, but hopefully it will get the point across. Where if you were to get like a different amount of mail on different days of the week. So if on Monday you get on average 5 pieces of mail, and then on any normal day you get only 2 pieces of mail, you could, and let's say you wake up in the morning or it's noon or whatever, and you don't know what day it is, you could get a probabilistic idea of what day of the week it is by checking the mail. When there's some difference in terms of how the amount of mail you get is distributed across the days of the week. So here I run through the math, which is exactly what I was saying. You model the number of pieces of mail you would get as a Poisson distribution, and then based on observing that Poisson, you could infer that it is, if you receive a lot more mail on Monday and you receive more, and you check the mail and there's a lot more mail, it's a lot more likely that'll be Monday. Then I won't get too much into the information theory aspect of it, but once we do the same math in log probability, there are different inferences you could make in terms of the amount of total information. So how encoding works is based on log probability, signifies the amount of information in any given event. For all of the exponential probability distributions, which is pretty much all the good ones, like Gaussian, Poisson, all of those, the math is really simplified when you move things into log terms. So that allows for a lot of cancellation. And yeah, you can generally simplify probabilities by thinking about them in log terms. So back to the autoencoder, how that works is you have, when I was saying you're like throwing darts, basically what that could be thought of as a stochastic embedding. So rather than specify, if you're given an example of something and you want to encode it, rather than specify exactly how you encode it, you specify a mean and a standard deviation of how it will be encoded, and then you draw a random variable here at psi, and you do the opposite of normalize. So you draw a unit Gaussian and then you multiply it by the standard deviation and add the mean. So that's a way to sample a unit Gaussian with a that's a way to sample a Gaussian with a specified mean and a standard deviation in a way that you could allow it to be backpropagated later on into an algorithm. This O is supposed to be an R. I'll fix that. So you set up this stochastic embedding. The interesting thing about stochastic embeddings is they're like, I don't want to be too speculative, but they're kind of like imagination. Because if you think of, I only know a little bit about brain architecture, but there's electrical synapses and chemical synapses. And chemical synapses are stochastic, where like a biological thing will occur and a certain number of neurotransmitters will pass through a synapse. So like, as far as we know, and again, I'm not an expert, so this isn't my stuff I know a lot about, but there is some stochasticity to how the brain works. So like there is some kind of random tumbling of dice or whatever in there. And additionally, yeah, that having a stochastic embedding allows you to frame a probabilistic model to generate new examples, if that makes sense. So yeah, the way this works is you decompose the amount of entropy, and you're able to create a lower bound on the probability that a draw from noise, draw from Gaussian distribution will generate a valid character. And just going back to the chart, so by regularizing how the embeddings can occur, you're able to increase the likelihood that you'll get a reasonable number whenever you draw from this latent space. And this is compressed down to 2 dimensions. It works a lot better if you say you have like a 10 dimension or even greater latent space. But autoencoders, partially because the introduction of noise reduces image quality. So once you want to kind of go into something like faces, it's a little bit tough to, yeah, they're just blurry. So they work well for handwritten digits, and when you have a small data and a ton of examples, but I think extending them much further was pretty difficult. So this is the actual paper that I based this on, was written by a guy out of the Netherlands named Kingma. It's worth a read if you're interested. I think GAN stuff has become really, really popular and is kind of getting the best results right now, but is really good and based in information theory and like encoding. So I think it would, yeah, I don't know if you're interested, I'd recommend reading the paper. Any questions on autoencoders?
Just to be very clear, what is the expectation taken over?
Oh, so that's, yeah, the probability that the decoding of an encoding of an example will recreate the example. So the expectation of that, would also be the cross entropy between your prior and your posterior. So on average, how well, with cross entropy as your loss function, how well are you recreating your examples?
basically it's an expectation of over embedding Z condition on given X, right?
I mean, it's expectation of your autoencoding loss. So like how much your image would, with what fidelity is your image reconstructed? We can check out the Kingma formulation as well. It is, let's see, it is this term here.
So it's the expectation of embedding Z given X.
Yeah, given an example digit. So like, yeah, this would be your encoding and this would be your decoding here.
Q is the encoding. It encodes X into embedding Z.
Let me just catch up with you. Yeah.
And P is decoded, right? Because Z into X.
Yep. So, yeah, I'd recommend reading the whole paper if you want to dig deep into it. But that's basically the principle. So you're autoencoding and you're forcing a constraint on your latent space to kind of make it generally follow a probability distribution. And what you're doing is maximizing the likelihood that a draw from that probability distribution will result in a character. And when you iterate through all of the given characters, you end up with this kind of manifold that's easy to sample from. So yeah, let's talk about GANs now, unless anybody has any more questions on autoencoders or anything. So generative adversarial framework is pretty cool. Basically, it's similar in a way, but has shown to be a lot more powerful. So what you do here is you have a huge training set of data, and then you have a generator. And the goal of the generator is to make examples, synthesize brand new things that are indistinguishable from the original training data. And then you'll also have a discriminator, which will be a separate network, or not totally separate, but it'll be a network with its own parameters, and its job is to discriminate between what is a true member of the original training data and what is synthesized example. So the loss formulation would be the log of the probability that, so first let's talk about the discriminator loss and kind of forget for a little bit that there was even a generator network, just that we kind of had two sets of examples, one of which between them. So we're rewarding it when it accepts or validates that an image is a real member of the training set when it is in fact a member of the training set, and it penalizes it when it accepts something that's synthetic. So that should be a pretty easy loss function to learn. You've got to whenever you get a new example, you don't know where it came from, and you have to say that either this is really from this training set or it's fake. Now the generator has a loss function which is the opposite. So what it's trying to do is maximize the amount of ambiguity between them two. I mean, ultimately it wants to totally fool the discriminator and have it accept only generated images and forget all of this synthesized images. So we have a zero-sum loss here. And so they're competing against each other, and the generator's task is a lot harder, but it gets full visibility into how the discriminator is thinking. So in terms of like activations and partial derivatives, it gets a full report card of, like, let's say it generated an image that looked almost perfect, but there was like, a big blue spot in the forehead. This is kind of a silly example, but like it could see the partial derivative with respect to that piece and learn how to, back propagate that through its whole network parameters. So it gets kind of like an audited report on how it did, and it's able to configure its own network to then learn to fool the discriminator even better. So you kind of get a point of convergence where you, so theta d, whenever we have theta, that's usually like the parameters of something. And again, this, we're just talking in general terms, but this, you know, theta would probably be on the order of millions of parameters. You minimize loss with respect to the parameters of theta d, and then you maximize that with respect to the parameters of theta g. So, yeah.
How exactly does this distinguish between like generated image and exact copy of the training set? How does it discriminate?
Well, it can't. I mean, those are just, you're saying they're totally identical pixel value. It doesn't know where things come from. So if it's the same pixel value, exact, yeah, it would have the same probability of being accepted in either firmware. Maybe I don't totally understand the question. If you were to generate the same thing over and over, the discriminator would learn that the generated image is fake. But I mean, if you could, with full variability, replicate the entire training set, if your generator was that good, yeah, that would be perfect. Because it has to go from random seed. So it can't have only like, you know, 10 images it generates. It needs to sample from a continuous distribution and then generate images. So if you didn't have enough data, then maybe that convergence would be possible. But if you have 100,000 images and let's say your batch size is like 64, you're having it look at each time, it would be really tough to get into that, you know, full replication mode.
That would be an issue in most of these cases.
Yeah, well, and if there's enough variability in the data set, I think it'd be a surprising, I mean, it would be a good problem, I guess, if you're having full replication of your training images and you're able to do some variability. So like, take for example, let's say you had 2 different training images and you sampled random numbers to generate each of them. In that embedding space, you could take the average of those random numbers and then generate something new. Really weird, like bifurcating and converging network going on. That new image would have to be, you know, some type of synthesis of those 2 images. Catch what I'm saying? Like triangulation in the embedding space should work. So as long as your embeddings are continuous, you should be able to generate new examples based on, you know, adding and subtracting or averaging embedding space. So the framework is pretty powerful, but training it could get pretty fickle. And the main reason is actually because the discriminator will get way ahead of the generator. And it would be like, I don't know, taking some like crayon drawing to an art expert and asking them how you can improve it to make it, you know, $1 million art piece. And they're just going to be like, I don't, you know, they're not going to be able to give you any advice because it's so ridiculous. So like you could get stuck where the generator is just putting out silly examples and the discriminator knows every time that they're fake. But the gradient, like, so even though the generator can see all of the parameters and partial derivatives and everything of the discriminator, there's just not enough information because the probability of the examples it's putting out being from the true training set are so little in the eyes of discriminator, it doesn't have much to tell it. So this paper came out called WGAN, or I don't know, like I think people would say Wasserstein. I probably would just say Wasserstein. But it's this mathematical framework that was utilized by Kantorovich and a lot of kind of measure theory and probability guys throughout the 20th century. And Wasserstein distance, but I won't bother you because it's a little bit of a nuanced thing, but it's really powerful in this instance because the original GAN framework is oriented around Jensen-Shannon divergence, which is basically the average of 2 KL divergences. And The illustration right here will show you that when you're really far away from a data set, it's not that informative to have Jensen-Shannon divergence as your loss function. You really need a true distance or a true metric function, and that's what the Wasserstein distance provides. Do you guys want to learn about that a little bit, or is it?
I would want some kind of like intuitive explanation of Wasserstein distance.
Okay, cool.
Like, is the problem that it's not a true distance metric? I don't think that's true.
I think Wasserstein distance is a better distance metric. I think the Jensen-Shannon distance is probably, I think depending on who you ask, it could be called a metric or not, but it's non-continuous at certain points. So the illustration is right here. Basically, if you had two parallel non-overlapping distributions, so you could say like your true data set is over here and the images you're generating are over here. The gradient between them, well, we just have distance here, but the partial derivative of this line right here would be a lot less informative than this line right here. And this is distance or an earth mover's distance, which would be, so that distance would be the distance between your parallel distributions. You're familiar with Jensen-Shannon divergence? Okay, cool. Yeah, I mean, it's basically like a denominator thing where it gets tough when, you know, in terms of log P, log Q, it can be a little bit difficult. Do you have a different understanding of it?
Yeah, this is like a weaker metric and has less condition and stable in terms of convergence. Like for normal GAN, when we talk about the argmax argument, the problem is that you have a lot of conversion problems, like there's like orbit solutions, it doesn't like settle nicely. For some reason, when you apply the distance, it has a, like, so normally when you're doing GANs, you're in like a Jensen-Shannon, you're in tail related to Jensen-Shannon.
Yeah.
In space, and that it's not a nice distance for the spacing to work. But somehow, like using the weaker condition of the EM distance, it makes it it's much easier for it to convert because there's like much.
Yeah, so I would agree with that, but I think basically those better properties are what's being illustrated here in terms of the, because when you're mentioning GAN gets like this weird orbital property where it never is really exactly converging, I think that, in my opinion, that occurs when you have your probability distribution of your training set versus the probability of the examples you're generating are just not overlapping perfectly, so they're able to be discriminated through, and yeah, your gradient isn't too informative when it's constant and then 0 and then constant again. But it is really informative when it's proportional to the distance between your probability distributions. So one Wasserstein distance, it gets technical. I'm going to try to give a little bit of an explanation of it, but basically it's an infimum between two probability distributions, which is distributions would be the greatest lower bound on the expected sum of absolute differences, which is the L1 norm, between samplings from the two distributions conditioned on the preservation of the respective marginals. So what this means is we have to like couple two probability distributions and kind of pair examples and compare them with an optimal coupling. And so like the L2 Wasserstein distance, which works really well for Gaussians and continuous probability distributions, is what I know a lot about. But you know, this the WGAN framework has a pretty brilliant employment of some properties regarding this one Wasserstein distance. So even that is like a simplified version of what's going on. But yeah, you're trying to find a lower bound on how well two probability distributions can be aligned. So the way to do this in practice would be to sample a really large number of both generated and training images. And by really large, I mean kind of like infinite, and then pair them one-to-one. So each training image has a counterparty in the generated images, and then calculate the average amount of change needed for a perfect match. So I don't know if you've ever done any work with like an Earth mover's distance in photography or anything, but that would have been comparing not full images, but comparing pixels across images. So the notion is, regardless of like how the generated and training images and what sequence they would be put out from the model, you generate a whole bunch of them and then align them optimally. You know, if you were to draw infinite, that would be a lower bound on how, you know, any of them could be optimally aligned.
What does aligning mean here? Because like we are generating different images, right? There's
Yeah.
not a corresponding like real image corresponding to a generated.
Yeah. Well, in theory, this is why, so this becomes non-tractable because we can't actually do this, but in theory, forever, and we could generate infinite and then pair them. You're getting at the right point though, which is why this Kantorovich-Rubinstein duality needs to be used, which allows you to take another angle to the same problem. And that's if you have something that's not a discriminator but a critic, and you constrain it to be Lipschitz continuous, which means its partial derivative needs to be fixed. And it can never have too drastic of a change with regard to any portion of the input. If it's Lipschitz continuous, the same one Wasserstein distance we had from the prior slide right here is proportional to the supremum, which is the upper bound, the lowest upper bound across all K-Lipschitz continuous functions of the expected score versus a true training set image. So it's a different way to calculate the one Wasserstein distance. And so rather than having to line up infinite of them, we can just do a sample over a batch. So basically you drop the discriminator. So now you have a critic. The output is not a probability of being from the training set or being from the generated set. And it has a positive value, but it's not, it's never going to be interpreted as a probability. And the parameters of C are optimized to maximally differentiate the synthetic and training sets. And you find the supremum by, once that converges, once you're able to, once you're not improving at differentiating the two image sets. So how do you enforce K-Lipschitz continuity? The initial paper had a pretty simple way. They were just clipping all the weights and parameters. So any pixel convolutional part of it could of the final outcome critic function with respect to any given portion of the image needed to be less than or equal to some value k. Then another paper came out where they found probably a better way to do that, which is to add a penalty to your loss function proportional to the norm of your gradient with respect to your image, the gradient of your critic's output with respect to your image, which basically makes it so it can't, have some type of like exponential reaction to any portion. Does that make sense at all, or am I kind of just talking nonsense? Okay. That's all I really had prepared. Oh no, we can talk about the BGAN. Yeah, sorry. I've got one more slide, and then we'll go to, I don't know, we should probably just machines a little bit. I think they're interesting. I just don't have the slides fully prepared. So boundary equilibrium GAN is it's a good way to end it because it deals with both an autoencoder and general GAN framework. But like we had a critic, which is a function. It's not, it's not outputting a probability. It's outputting to auto-encode something. So the ability to take in an image and then take it to an embedding space and then regenerate it. So if the autoencoder is really good at auto-encoding real faces, something that doesn't look like a real face, it has trouble auto-encoding. So it's like it's got to take a face and compress it down and then regenerate it. So using this as a critic allows another way to kind of like learn embeddings inside of your critic and then apply those to differentiating training examples from generated examples. And then because this is so efficacious, you know, I guess the logical conclusion would be that the information of that gradient back to the generator is really, really valuable, and they're able to generate. So this is the same thing we were talking about on the very first slide, where it's the 360,000 celebrity headshots and I think it was like 17 million parameter network. And this is a kind of cool diagram where they do math in the embedding space. So they're taking, on the far left, I think these are real celebrities, I'm not sure. But they're linearly interpolating between them. So them gets embedded and then how another one gets embedded, and probably linearly slicing that up into 10 steps along the way and then generating the images that would be produced from drawing those specific random numbers anywhere in the embedding space.
Do you know if it has been tried on the standard data sets like bedrooms and ImageNet, this particular gap?
Yeah, I mean, it has been tried on specific, we'll pull it up. Oh, will this kill the, if I open something on the internet, will it kill the broadcast?
No.
Okay.
You would just need to select a different window to broadcast.
By the way, these pictures are made on the private data set.
Yeah, that's correct. I mean, so I think, you know, there's that like Celeb A data set, which has something like 100,000 pictures of celebrities. They wanted to extend it. So they say somewhere in here that, yeah, they did a data set of 360,000 celebrity face images. And that could be the reason it works a lot better. But
The reason I find it is a bit hard to compare.
you're right. Yeah, I mean, it may not be apples to apples, but I think the results are definitively better. And they're not, they may be cherry picking a little bit, but it's really tough to do this if your model only works in certain specific examples. I think linear interpolation is kind of a definitive way to show that the thing really works. But I think that is a fair point. This was probably pretty high power. I think they said they trained this network for like 2.5 days or something. So it might not be apples to apples with other networks. Like maybe a little bit more energy was put into making this one really good. But it's tough to say.
And the second question, it really looks like WASSERSTEIN-GAN.
I'm sorry?
It really looks like VGAN.
So frankly, I think this is a form of WASSERSTEIN-GAN, if you ask me. I think they approach it in a little bit different way, and they use like a regulator that the guy, he just mentions that he figured it out from control theory, but basically it's a way to scale how well your generator learns with a this parameter k, which calibrates on how the generator does versus discriminator. Other than that, I think it's basically WASSERSTEIN-GAN.
The loss function is only, the discriminator is always positive, right? No negative. Which means that
In this instance, yeah, as is true with the WASSERSTEIN-GAN. Yeah.
there's a constraint that WASSERSTEIN-GAN is pretty faster than positive.
I can double check, but I'm pretty sure. But well, yeah, this would be positive because it's an autoencoding loss, so there's an absolute value in there. So yeah, I mean, I'll have to think about that. But this one, it definitely is constrained to be positive, and I think it's basically K-Lipschitz. So I think a lot of the same logic applies. They constrain that they're, you know, the ability to autoencode in a really good way to learn embeddings, and it just so happens to give very valuable gradient information back to the generator.
Where do you think WASSERSTEIN-GAN means non-negative?
Why did I think of this video? So there's no energy function, but why does it need to be why does the critic's output need to be non-negative? I have to think about that again. Yeah, actually, you might be right that it can go positive and negative. Yeah, but it's definitely not bound in terms of being a probability. You know, you always need to be between 0 and 1, which is the original GAN network. But
I have some questions for one.
yeah.
Okay, so someone is asking, and it's about GANs and Wasserstein-GANs. Is the distribution of the latent space important? And what if this, if we sample Z input into a generator from a uniform distribution, not a Gaussian distribution?
That's totally fine. Like, so the latent space is important, but they're pretty interchangeable. Like, so uniform, you're bound. You need to be like within a certain area. And Gaussian, you know, you're not bound. Other than that, I think it's a little bit of personal preference. For example, the example I'm showing right now, boundary equilibrium GAN uses uniform sampling.
I have one more. It's okay. So, what is the root cause of mode collapse in GAN? Among GAN, Wasserstein-GAN, and VGAN, which one is the best to avoid mode collapse?
I guess I have to know exactly what they mean by mode collapse. I think I know what that means, which would be that, is there any way we can ask them a question? So by mode collapse, do they mean convergence of the generator on a specific? Actually, what do they mean by mode collapse?
So I just asked him to reply, and then maybe once he gets
Yeah.
back, we can
So
come back.
mode collapse is a very common GAN problem. It's mentioned because also it basically is like what you said. It just converges to a particular image, which is kind of like a mean of the training images, which could pass.
Okay, cool.
Which could pull the discriminator. So
Okay.
it's a common problem with the GANs until like the improved GANs paper actually had some improved. WGAN and VGAN kind of like avoid this problem. But I don't know which one is the best.
So yeah, my intuition on that would be just not, once you move out of a log prop framework, so you move away from Jensen-Shannon divergence as your framework, I think you avoid it. But I don't know. I guess I don't. Yeah, I'd have to, maybe I can get back to him.
I can offer my theory.
Yeah, yeah.
If you train generated too much, you try to basically find the maximum of the discriminator, right? And then you get the call.
Maximum of a discriminator in a probabilistic framework or in a critic?
Well, basically, to find generate one X, which has the biggest result if you just generate too much.
In which framework, though?
If you train too much generator. Now, if you train too much discriminator, then in Wasserstein-GAN, it gets better. Regular GAN, you get very good discriminator, but without gradient for your generator. So basically, overtraining discriminator in Wasserstein is good, and it's kind of good in GANs, but if you do it too much, there will be no signal for the generator.
Cool. I definitely agree with that. And I think that's because the Wasserstein-GAN is almost predicated on having a really strong critic in order to provide an accurate distance. You need to take, you need your critic to be really optimized to have the valuable gradient.
So the cool thing about VGAN is that it also balances out the generator. So using this proportional control makes sure that generator won't.
Yeah, I agree with you. I just couldn't figure out all the method to the madness of how these, you know, how gamma and lambda are chosen. And I think I know K kind of regularizes things, but I don't have full intuition as to like how he came up with that regularization parameterization.
So another way you could regularize the generator is to add entropy of the generator. It's really hard to get rid of entropy. good.
Great.
Yeah, that's all I got.
Great. All right. Thank you. Oh, sorry.
Which one of them is actually used?
Well, I think where? Like by whom?
In real world.
Yeah.
I'm writing papers.
I don't think there's any consensus. There are like 100 GAN papers out there right now. Like every month there's a new GAN which it says better than the previous.
I think WaveNet, which now is kind of in production, right? It is actually neither. It's like a new edition kind of model. It's basically the current conditional explicit model.
But that's not a voice, right?
And similar thing for pictures, for pixels. And it basically has a tracking probability density. And some crazy people at OpenAI managed to take pixel CNN and put it into variation autoencoder. So we generated the pixel CNN, and we can still get latent vectors using encoded. With the mix and match inclusive paper.
Cool. Yeah. So these are 4 options. You can do whatever you want. Nobody's going to stop you. All right. Me?
Yeah.
Oh, I've messed around with some of these. I've done some things related to Wasserstein distance, but I don't have anything like definitive. So basically what that means is you're using a different norm here, which for certain continuous distributions. Here we're dealing with all these crazy complex manifolds that are really difficult to when you have certain symmetries of your distribution, like for example, in this instance of Gaussians, you can use a little bit of different math. And I don't have any good results right now, but maybe someday. Yeah, but so that's unrelated. So that, yeah, I've done, I put up, it's on my GitHub. If you want to check it out, I should probably update it because I've done some other stuff with it and I haven't put those up. But basically, so there's no GAN in style transfer, but that what's up? Sure. I can, I think I can get my browser. So let's see what's going on here.
Do me a big favor and select the videos that you're showing because I think you're still in the presentation. Like if you can
Gotcha.
take it out.
Yeah.
So that's me. If you go to the green, yeah.
Sorry, this guy?
I think you were in the right space, but I think it's in the middle window that you, or this one. Wait, isn't your GitHub?
So that was my GitHub. This is on Cognito. Do I need to go here?
No, you were right. You were about to select it. Yeah, I led you astray. I think now it should be. It's a little delayed by a couple seconds.
So, all right. So all those big formulas we dealt with, when you know, let's see.
Can you come back?
Yeah.
So yeah, screen share and then. Nope.
I think you turned on.
Yes, great.
Okay, so there's some closed form solutions. that'll allow you to calculate two Wasserstein distance. Here it is. I was hoping this would be a little easier. So when we're talking about the distance between probability distributions, when, for example, when we have Gaussian or something where the math works out really well, we can come up with a closed form definition of a distance. So by taking a pretty generic network like VGG and you apply it to a picture like this, so something that's really stylized with a bunch of features, you could think, so VGG has a CNN which looks at specific pieces of an image through convolutional windows and basically takes the red, green, and blue pixels from how they are in an image to like a really abstract feature space. And so then that feature space is represented in various spots across the image. So you could think of each of that feature space as a random vector and then look at the distribution of how it changes across an image. So that distribution, the mean in covariance of all the different filters, you could say describes the visual characteristics of an image. So we could take, so basically what this does is it takes any generic computer vision network to feature space and describes the average activation and then the covariance, so the first and second moments of the activations as a multivariate Gaussian. And then between Gaussians, we can calculate distance and we can backpropagate distance and make images converge. So if we take this image of a cat and we quantify, a probability distribution around the of any given, filter in I'm using VGG here, but it could be any computer vision network. Then we also quantify how they covary. Then we look at an image like this this lion, and we basically give the computer a task to change this image of this lion, minimal changes to the picture of the lion such that the distribution of visual characteristics across the page is similar to the one of this cat. Then we'll end up with something like this. So you can kind of transfer visual characteristics that way. So it works pretty well for like if we do Van Gogh. You can see it there. So it uses L2 Wasserstein distance, but it's very different from Wasserstein-GAN because you're assuming a parameterization. You're saying even though I'm taking all this real data, I'm going to just look at the means and covariances across, say, like a 512 dimension feature vector, and then change another image as minimally as possible such that it represents those in aggregate. So I've been planning to update this file with a better explanation. There isn't much on there, but hopefully within another week or two, if you check back, I should have better explanation and some better examples. That kind of makes sense at all?
How do you enforce the confidence? Can you compare high-level features?
Yeah, I compare all the features. So if it works well, you can start from any starting point. Like, with that picture of the cat, there's a picture of a landscape, and we could take the visual, this is like, has nothing to do with a cityscape, but somehow we get motif or texture onto, a picture of a city.
So what I was asking is that you have this original feature, right?
Yeah.
And you generate an image with statistics of certain filters matching art. But you also need to make sure that the picture generated matches the picture of the cat. How do you enforce confidence in that?
well, I disregard it, I guess. I mean, I don't enforce content similarity. So like in that initial style transfer formulation, this is doing the exact same thing in terms of taking an image to a feature space of the activations of a neural network. I guess the step I'm taking that's a little different is conceptualizing it as a random vector across the image, making that assuming that the first two moments of that probability distribution fully explain it is the same as assuming it's a Gaussian. So I do that, and then I take the L2 metric between those pretend Gaussians, and then cause those to converge, and that's what brings the feature vector together. So in terms of content, I'm not totally sure what you mean. All I care about is the distribution of activations.
You said you wanted to change the pixels as low as possible while still maintaining the space distribution. So that would change that would keep the content of this similar.
Oh yeah. Okay. Cool. That might be the answer if that's the question was totally. But that is definitely what I'm doing. So I'm saying, if you ever heard of optimal transport, if you have a metric, a distance between two probability distributions, the derivative thereof is a transport plan that happens to be the optimal way to get from one place to another. So that's what I'm doing between these two pretend Gaussians parameterized by the mean and covariance of the filter activations across the image.
So in feature space, is that like at every layer, or is that at the very end of the network? Could you somehow like compare the feature space only after the first layer and only make?
Yeah, you can. Yeah, you can. So if you do every layer, just heuristically, they're pretty redundant. If you do like every third layer, it looks almost as good as if you did every layer. So that's what I generally did. If you take a really early layer, let's say, before any layer, if you were to do the same thing with colors, you could do it without any neural network. Just apply that statistical, the distance collapsing I was talking about with colors, and that would color match. Then the first layer would be very basic features like the amount of edges or whatever, and then once you get to deeper layers, it would be like brush strokes or kind of broader texture patterns, and then the deepest of the layers would be like kind of these more ethereal, I don't know, you've seen deep dream stuff. It's like it gets a little ghosty. All set?
Yeah, so I know like the most popular application of GANs is images, but do you know if there are any other domains where they're used or experimented with?
I think people have tried with audio. I think it's a little mixed right now. If I made good slides on Boltzmann machines, I was going to talk about embeddings there. So those were used, it seems like a long time ago. In 2007, Netflix had this big contest for building on movie recommendations. So you have a whole bunch of people that watch a certain number of movies, and then you want to find a way to figure out, to propose to them other movies that they may like. So that used Boltzmann framework, where you're kind of learning these embeddings, and then you're able to generate new. It's as if you're learning how a person with certain characteristics that has reacted in certain ways to some set of movies would react when they see these extra movies. So you're kind of generating this like fake movie experiment, and then using that to predict what they would actually like. So that's the only, that's the most like practical thing I can think of that uses these generative models. But someone else might know of something else. All right, thank you.